Hey everyone, I'm Joey. It's my great pleasure to welcome you to the keynote of Research Week. I'm particularly delighted to welcome Professor Kuldeep Meel. He is Sunkaki Assistant Professor in SOC. He is an affiliate at the Institute of Data Science and also hold a long-term visiting point at the Computer Science Department of IIT Bombay. His research interests are at the intersection of artificial intelligence and formal methods, which also lies at the intersection of theory and practice. So let's welcome Professor Kuldeep's speech.
Okay, I hope you can hear me, right?
Yes, we can hear you, Prof.
Okay, good. Thanks a lot for the introduction, and let's get started. So I'm going to discuss the work that we have been doing over past decade or so about a problem called model counting. I'm going to discuss what it is. I'm also going to discuss how the problem was motivated by something else, an exciting development at the intersection of AI and formal methods. So let's get started. And I think before I get into the technical details, it's one thing I really want to acknowledge is a tremendous effort that has been put on in putting up a really nice program, despite there being such a pandemic situation. So congratulations to Yachi, Nitya, and the entire team for putting together such an exciting program. For most of you who are first year PhD students, I hope this would be a good motivation for you to see that how your senior PhD students are able to put together such a wonderful program. Also, all the work that I'll be discussing, this has been a large project over past few years. So there has been lots of collaborators across the world, and it's very important that I acknowledge all of them, including my brilliant students here at NUS. Okay, so let's get started. So let's start with the problem of Boolean satisfiability. So what is the problem of Boolean satisfiability? Well, in very simple terms, let's say we are given a Boolean expression where we are using operators such as AND, or not. And the problem of Boolean satisfiability is to ask, is there a satisfying solution? So is there an assignment of zeros and ones to the variables that make the expression evaluate to true? So for example, here is a simple expression that I have listed here. We have what we call as clauses. So clauses have variables or their negation, and all of them are joined together by disjunctions or ors, and all of these clauses are joined together by AND. This is a one particular normal form to represent such Boolean expressions, but you can express in any other general form. So the problem of set is to say that given such an expression, is there a satisfying assignment? So if you look at it this long enough, I guess I hope all of you will agree with me that assigning x1 and x2 to 0 and x3 and x4 to 1 would make the expression evaluate to 1. So one thing I wanted to mention, I really would like this talk to teach you some of the things that we have been looking at. So if you have any question at any point, please raise your hand or ask the host to ask questions on your behalf. Okay, so please don't wait till the end. We have plenty of time in the talk to take questions as we go along. Okay, so this is a simple problem. I'm sure most of us look at this problem sometime in our high school, and it's no surprise that there has been work on this problem going at least 200 years. So here is William Jevons, who was famous for marginal utility theory. He also, in my view, introduced kind of the first computer. He introduced this logical piano. And as he's giving this piano out so that the others can compute using such a machine, the way he's advertising is that he has paid a lot of attention at describing this device that can do simple ors and ands together. And he thinks that this is going to save the trouble and risk of making mistake. And Schroeder, who is typically credited as father of modern mathematical logic, goes on to claim that finding the fastest method for obtaining an algorithm for this Boolean satisfiability would be the ultimate goal of mathematics and logic. So this is quite a tall order if you think about you are in the 19th century, and this seems to be the ultimate goal of mathematics and logic. Some of you might know the story. Well, the story has a bit of a tragic end in one way. Cook and Levin in 1970s independently showed that the problem of Boolean satisfiability is NP-complete. And what this entails is that it's been almost for 50 years since the seminal work of Cook and Levin, and we still do not know if there exists a polynomial time algorithm. So in some sense, the fastest method looks like an elusive goal and maybe something we may not be able to ever achieve. In fact, Clay Institute a $1 million award for the problem of Boolean satisfiability. And some people joke that this is the quickest way to make $1 million if you are doing pure theory. Okay, so on one end, you look at the sequence of events and you might believe that, well, there is not much to this problem we can do. But at the same time, starting in late 1950s, very exciting developments have happened. So Davis and Putnam, working for National Security Agency, wrote one of the first reports, which was followed up by Logman and Loveland in collaboration with Davis. And the entire algorithmic framework that came out of these efforts is called DPLL. So what is this algorithm? Well, this is kind of something, again, we typically see in our high school. So how does it work? You have a set of Boolean variables. You pick one of the variable, you assign a value to these variables, and then you see that, well, does it propagate something else? Does it from this, can I deduce that certain other variables should take a fixed value? If yes, you do the propagation. At some point, you might detect that, well, the current assignment does not satisfy the formula. So you go back, you again keep doing this until you either have exhausted all the possibilities or you have indeed found a assignment that satisfies the formula. So let me give a quick example. So let's say this is the formula we have over 4 variables, x, y, a, b. So I'm going to just, so that we can remember what iteration of loop iteration we are talking about. So I'm going to use word level to denote that. And the second column is going to indicate what is the decision we have. So initially we start, we say, well, from this formula, can we deduce directly that some variable should take a value? It doesn't look so. So we go back and we assign x to 0. If we assign x to 0, then this clause is satisfied. Okay, we can go and assign x to 1. Then we assign y to 1. Okay, this clause is still satisfied. Now let's say we assign a to 1. Well, what happens? If a is 1, then look at this clause. Okay, so all of these clauses must be satisfied for the formula to satisfy. And if a is 1, then b must take value 1. All right, so let's try to figure this out. So if a and b both are 1, then you look at this clause. This says, hey, you can't make a and b both to be 1. So we have to backtrack. We have to say, okay, so assigning a to 1 was a mistake. So let's try to assign a to false. Well, if a is false, then you look here, b has to be 1. But then again, if a is false, then this clause says that, hey, b should be 0. So that was again a mistake. We keep going back, we continue to do this, and until we finally realize that, well, we are not able to make any assignment. And that satisfies the formula. But you saw that the process, although it's a little bit more intelligent than it would be if we had just picked a random assignment, it still seems to take exponential amount of time. And this was the story for next 30 years. So remember, we are in 1960s right now. Davis, Putnam, Logman, and Loveland proposed this method. And for next 30 years, we basically could not find anything that works better. So you go back to 1990s, and this is in cold weather of Ann Arbor at University of Michigan, a PhD student enters. And this PhD student is again trying to look at this algorithm and trying to understand what's going on. So let's look at slightly different formula here. So we have this formula. Again, we are going to make assignment to x. If we assign x to 1, we kind of see, okay, we cannot deduce anything. If we assign y to 1, okay, things are fine. Let's say we assign g to 1. So you look at this clause, right? So we say that x and g are 1. This implies that a must be 1. Well, if a is 1, then we look at this clause. This one says, well, whenever a is 1, b must be 0. Okay? The clause here, so we want to indicate that x and g, both of them imply a, right? Because this is the clause that is making us to assign a to 1. And then we also want to say that whenever g is 1, then b must be 1. So we got a and b both to be 1. But at the same time, you remember, if we assign a and b both to be 1, we get a conflict. So what we would earlier do, we would say, hey, making assignment g to 1 was a mistake. Let's try to fix it. But then Joao Marcus Silva, the PhD student that I talked about, is looking at this graph and says that maybe we can deduce why did we get into a conflict in the first place. It was not just merely assigning g to 1 after assigning x and y to 1. If you look at this graph, y plays no role in it. It's only the assignment to x and g that are getting us to the conflict, right? So if I want to remember that, never make such a mistake, what I would try to remember is that never assign x and g to 1, okay? So the reason is that x and g should not be 1 at the same time. How do I remember something like this? Well, I can create a clause. What is a clause? It says not x or not g. And I'm going to remember it in future so that whenever I assign x to 1, it immediately tells me that you have no choice but to assign g to 0. Okay? So this was a major breakthrough. And of course, if you have studied something called resolution, then you can see that the close learning can also be derived using resolution, which is essentially you take these 3 clauses and you will be able to see that we would be able to derive not x or not g. So a very important part that I really like about this story is for 30 years in a field, not much has improved, and then a PhD student enters and is kind of making a observation, looking at the core basics of what's going on, and then be able to inspire from this and come up with an idea, which is really learning something, right? You want to learn new clauses. And then you can add these clauses and continue the process on. And then fast forward. Of course, once you learn this clause, then you go back. And as I mentioned that whenever we assign x to 1, g will be equals to 0. And we go on, so on. Okay. Of course, this was late 1996, 1996 when the paper was published, and now there has been 20 years of lots of work and lots of ideas. One is how can we improve the clauses we are learning? Sometimes, just like all the things in life, sometimes you may just be taking wrong decisions, so it's better to restart, and we have come up with more sophisticated data structures and so on. So where are we now? Well, in 2016, Don Knuth, who is one of the leading computer scientists, a Turing Award winner, wrote an entire book on satisfiability. And in this book, there are just about 2 pages devoted to the NP hardness, and rest of the pages are devoted to how these set solvers work efficiently. And he put it very nicely. He says that the modern set solvers are able to deal with problems that were regarded as hopeless just about a few years ago. As I speak, the solvers find applications in a wide variety of areas, such as if you want to do a telecom feature subscription, well, there's a set solver running behind for planning, noise analysis, games, model checking, and so on. And at this point, about 8 years ago, we said that, well, now that set is easy, it is time to look beyond satisfiability. Of course, here the word easy comes with a qualification. I don't mean to say that for every formula out there, we can always efficiently solve the problem of satisfiability. It's easy for the problem that typically arise from practice. And this is a theme that keeps coming back again and again in the entire line of work. So this is how we got started. But of course, the idea about to look beyond satisfiability has been in the air for last 15 to 20 years. There are lots of other people who have been also inspired from the fact that the set solvers are easy, has started to look for problems beyond satisfiability. So what is the problem that we wanted to look at? Well, the problem is of counting. So initially we had a set of variables, a formula over these variables. Let me introduce a little bit of notation. Let's say sol of f is the set of solutions of this formula. The problem of satisfiability was to ask, is there a satisfying assignment? So is there an assignment to these variables such that it satisfies the formula? Or in other words, well, is this set empty or non-empty, right? Now we can start talking about properties of this set. So we can ask, how many elements are in this set? So the problem model counting is to determine the cardinality of sol of f. Let me give an example just to make sure all of us are on the same page here. Also, before I get to the example, one more thing. So we can also put a weight function over the assignment space. And now weight of a formula becomes weight of the sum of the weight of the solutions of this formula. And the problem of counting now becomes determining the weight of the formula. So let's give a quick example. Okay, so we have a formula f, which takes x1 or x2. Let's say the weight function assign weight of 1 by 6 to 0, 0, and 1, 1, weight of 1 by 3 to 1, 0, and 0, 1. And now the set of solutions of this formula are essentially all the three assignments except 0, 0, right? So we have three satisfying assignments, which are 0, 1, 1, 0, 1, 1. And of course, 0, 0 is the assignment that does not satisfy. So what will be the weight of this formula? Well, use the sum of the weight of these solutions and it comes out to be 5 over 6. Okay, so I hope the problem is clear. I give you this formula x1 or x2. I ask how many solutions are there? 3. What is the weight of this formula? 5 over 6. So this is precisely the problem of counting that we are interested in. At this point, you might ask, why should we care about this problem? Well, it turns out to be a very fundamental problem in computer science with wide variety of applications. In the interest of time, I'm going to focus on two such applications. In the first, I will discuss the application of testing of AI systems. And the second application I'm going to discuss is the problem of network reliability. I will show how these problems reduce to the problem of model counting. And then I'll discuss the hashing-based framework that we have been developing for past few years. So let's get started. So as most of you know that there has been a lot of progress in the design of these machine learning systems. And with progress comes the opportunity of adversarial agents trying to do malicious things. So it is important that we could verify that such malicious behavior will not happen. So that the methodology for verification is that we are given a model. So we are given a neural network and an image. And let's say one of the problems that we are interested in is to ensure that for every small perturbation, the model should not give different answers, right? So this is kind of a standard standard scenario that we have seen in lots of times. You take an image, you make some small perturbations, and then the network can give very different answers. For a long time, we used to think that we will be able to really design system that would not make any mistake, but seems like the evolving viewpoint is that we will have system that will make some mistakes and they are acceptable. So now the viewpoint is that instead of checking whether there exists such a small perturbation that can make the network change its output, we are interested in ensuring that there are not so many such small perturbations. So now the problem of asking is from whether there exists to count how many such perturbations exist. So this is what we did in our paper last year, is to show that we can reduce the problem of computing how many such small perturbations can trick the network to make error, and that reduces to the problem of counting. So how do we do it more formally? Well, we are given a neural network. We have a property. We can encode the property by saying that, well, this neural network takes, let's say, X and XB. These are the two inputs that differ over K bits. So a small perturbation, and we would like to ensure that the outputs are not different. So this is our final specification. And at this point, we would like to check, well, how often the network makes such mistakes or not. Another application that we looked at is, here is, which was motivated when I was in Houston. So here is the city of Houston. And as you can see, that city of Houston looks beautiful at night, but the city of Houston is prone to hurricanes, and these hurricanes cause havoc. And this requires operations that are resource intensive and very critical. And one of the important problem that we have been looking at is, can we predict the effect of natural disaster on critical infrastructure such as power grid? In particular, we are interested in predicting likelihood of a region facing blackout. Let me put the problem in more computer science context. So on the left, we have a graph where nodes corresponds to the stations that generate power, or the nodes or the places that consume power. So let's say we have some source node that generates power, some terminal node that we are interested in. We can model the failure probability by assigning probability to every edge. And the problem now is that to compute what is the probability S and T get disconnected. The key idea is that at every point in time, we can represent the configuration of a network using a vector of size E, which is a set of all the edges, so that the weight of this configuration is the probability of observing the configuration. Once we are interested in the configurations where S and T are disconnected, we can represent this using set of constraints over as variables. And once we have this set of constraints, then the problem of computing S and T are disconnected just simply reduces to summing up weight of all the solutions. And remember, this is precisely the formulation of counting, right? You have a set of constraints, a weight function, you want to sum over the set of solutions to this set of constraints. Okay, so of course, this is a fundamental problem, and there has been a lot of work in the past. And what motivated us is this seeming divide between techniques that have very strong guarantees, but often scale to very small instances, while the guarantees, while the techniques that have weak guarantees, but can scale to large instances. And the overall goal in our project has been, can we bridge this gap between theory and practice? So I'm going to discuss some of the work that we have done here. So again, going back, we have a set of Boolean variables, a formula over these variables, a weight function over the assignment space. The problem of exact counting is sharply complete. So we are going to look at an approximate version. So where in addition to the F and W, we are given two parameters, epsilon and delta. And we would like to compute an estimate C, so that C is within 1 plus epsilon factor with probability at least 1 minus delta. As a first step, we were able to show that we can reduce the problem of weighted, we can get rid of the weight functions. What do I mean by that? Well, given the formula F and weight function W, we can convert into another formula F prime, so that the weight of F is a constant that depends only on W multiplied by the number of solutions of F prime. And now what we are left with is that how do we estimate the number of solutions of this formula F prime here? Of course, as we go in more details, the way we do this reduction is that we will have to encode the weight function as a set of constraints, and the new formula that we get might be larger. So these are interesting problems that one can look into in future. So going back, how do we estimate the number of solutions of this formula F prime? Let me give an example that might be more closer to heart. So let's say, suppose we want to count how many people in Singapore like coffee. So the population of Singapore, as I checked this morning, looks like 5.6 million. Well, we can assign every person a unique 23-bit identifier so that we are covering everyone. So suppose I asked you this question. How would you go about counting how many people in Singapore like coffee? Well, one idea can be we pick about 50 people, we count how many of them like coffee, and we multiply our estimate. What can go wrong with this? Well, if only 5 people like coffee, then it is unlikely we will find anyone who likes coffee in our sample of 50 people. Okay, so what can we do here? Well, this is where we would like to use the power of set solvers. So what is a set query here? Kind of the analogous set query is that find me a person who likes coffee, right? Find me an assignment that satisfies my constraints. So you could ask a set solver, find me a person who likes coffee. Find me a person who likes coffee and that person not person Y. So if there are only 5 people, then the idea is simple. You ask for person 1, then person 2, person 3, person 4, person 5, and you are done. But what if everyone likes coffee? So the idea about just using a set solver and making all the queries would not work really well in practice. So essentially, the real question that we have to handle here is that can we do with lesser number of set queries? Can we make maybe linear number of or logarithmic number of set queries? So let me quickly give you an overall idea about how we went about addressing the problem. Let's say the circle is the space of all possible assignments and the dots represent satisfying assignments. So wouldn't it be nice if we could partition the space of solutions into cells such that the number of solutions in every cell is roughly equal and the cells are small enough? Remember, the issue was that we could not use a set solver to enumerate all the solutions if we had too many solutions. But if the cells are small enough, then we can go and pick a random cell and we can enumerate all the solutions in this cell, and our estimate will be total number of solutions in a cell multiplied by total number of cells. Will this work in practice? Let's check it out. How are we going to get there? Well, the first thing we need to address is how do we partition into roughly equal small cells of solutions without knowing the distribution of solutions? The second challenge is a bit subtle but will become clear very soon is how many cells do we have to partition into? So to address the first challenge, what we are interested in is designing a function H that maps assignments to cells. In computer science context, we call such as hash function. So solutions in a cell alpha is conjunction of all the solutions of the formula conjuncted with all the assignments Y that H maps to alpha. As you can see that if you have a deterministic function, it's a bit unlikely to work because you can think of like some adversary will put all the solutions in one cell and the ideas will probably not work. So this is where we use the power of randomization. And the idea is that we are going to construct a large family of hash functions so that if we choose one of the hash functions randomly from this family, it's going to be able to do the partitioning with a high enough probability. How does this look in practice? So what we are interested in is what is called the family of 2 universal hash functions. So what are these 2 universal hash functions? Well, it says that for every pair of 2 assignments and every pair of cells, if we pick a hash function randomly, then the probability H maps Y1 to alpha 1 is same as probability H maps Y2 to alpha 2, which is 1 over the number of solutions. Furthermore, these events are pairwise independent. So the probability of H mapping Y1 to alpha 1 and H mapping Y2 to alpha 2 is just the product of the marginals. What do pairwise independent hash function give us? The random variable that we are interested in is the number of solutions in a randomly chosen cell. It ensures that the expected number of solutions is total number of solutions divided by total number of cells. Furthermore, the variance is small. In particular, variance is less than expectation. Where are these 2 universal hash functions? Let me give you a standard construction of these universal hash functions. So let's say we have variables x1 to xn. We want to construct a hash function over the space from 0, 1 to the n to 0, 1 to m. So to do that, we choose m random XORs. How do we choose every XOR? We pick every variable with probability half, we XOR them together. As you can see, in expectation, we'll have about half of the variables in XOR. To choose a cell randomly, we set each of these XORs to 0 or 1 randomly, and now the solutions in a cell is essentially the formula conjuncted with all these random XORs that we have constructed. One of the challenges that comes in here is that the performance of the state-of-art set solvers degrades with increase in the size of these XORs. Remember, as I told you that the solvers cannot handle every kind of formula. So this is a major challenge that we had to overcome. I won't have time to go into more details, but one quick idea that we were able to use is to say that, well, we don't really require all the variables to specify the solution space. So we can just concentrate on a subset of variables. And the key idea was that how do we have to find this subset of variables? And for that, we proposed a process that reduces the problem of independent support to that of minimal unsatisfiable subset. It's another problem known, and this can really lead to a strong improvement in the runtime. Let's go to addressing the second challenge, which is how many cells do we partition into? For that, a small technical definition, we say a cell is small if it is about threshold many solutions. So we are interested in partitioning into the number of cells, which is 2 to the power m star. So we would like the number of cells to have roughly threshold many solutions. So that would require us to have the number of cells to be number of solutions divided by threshold. And this looks like a bit of a catch-22 because we wanted to estimate the number of solutions. And now I'm telling you, if you tell me the number of solutions, I can tell you how many cells to partition into. So how do we address that? The idea is that we check for every value of m that if the number of solutions in a randomly chosen cell is less than or equals to threshold. Let me show you more graphically. You start with the formula. You ask, is the number of solutions less than or equals to threshold? The answer is no. You partition into 2 cells. You pick one of the cell. You ask the same question again. If answer is still no, you partition into 4. You keep going it until you reach a point where indeed the number of solutions is less than or equals to threshold, and your estimate is total number of solutions times the total number of cells. Is this going to work in theory? Turns out yes. We were able to show that the estimate you are going to get is going to be within 1 plus epsilon factor with confidence at least 1 minus delta. How many set calls we make? Well, we have to make only logarithmically many calls to the set solver. And this is very important. Remember, the number of solutions can be exponential in n. It can be almost 2 to the power n. And now we have to make only log n calls to the set solver. If you are interested in more theory, it turns out that if the formula is in DNF, which is in disjunctive normal form, then the algorithm that I just described gives you a fully polynomial randomized approximation scheme. All right, so that's good for theory. How well it works in practice? Let me case on one example of interest. So here's the power grid from one of the cities in South Carolina. We number all the terminals. We want to compute what is the probability a terminal is disconnected. We take the state-of-art tool that is used in practice, and it times out after 1,000 seconds for each of these cases. The algorithm that I just described can consistently compute estimates within 150 seconds. This is result for one city. Of course, we have results for lots of cities, and this generalizes very well. How accurate estimates we get? Well, we took another example of a city where we could actually get the ground truth. And then we ran our algorithm with setting epsilon to 0.8. And here is what we observed. The estimates we get are really very accurate, much better than what we can guarantee in theory. So there is still a gap between theory and practice, something that would need to be addressed in a future PhD thesis. Okay, so what about the neural network example? Again, we take different neural networks and we can compute how many adversarial examples you have or the fraction of adversarial examples. And it's worth remarking that the prior state of art would time out on all such instances. So this progress that we have made over the past few years is really showing in its ability to handle practical problems. Of course, I just discussed 2 applications. There are lots of applications. I would be very happy to receive email from you and talk in person later on. There are applications in problems like synthesis, probabilistic reasoning, quantified information flow, and so on. Okay, so let me conclude. I want to talk more about a story here. The first 20 years since João Marcos Silva's remarkable insight allowed us to build set solvers, and these set solvers were able to solve problems that were regarded as hopeless, paraphrasing Don Knuth. And this gives us opportunity to build on top of this. And we can now start looking at quantifying these problems. I had discussed one problem. There are lots of other such problems, and these are all very fundamental problems. When you work on these fundamental problems, the applications come from wide variety of sources. When we started working on this project, we did not know about all these applications. As we continue to push the algorithmic frontier more and more, we get exposed to more and more applications. These tools are all open source, so we get emails, contacts from lots of people who say, you know what, now I can reduce my problem to counting. So far, there was not a very scalable tool, so I was not able to use it, but now there's a scalable tool. I would like to reduce my problem to counting. So in last 8 years, I think we have made improvements, and over the time we have seen that we are balancing both scalability and the performance. So we continue to push the envelope for this frontier at the intersection of scalability and performance. But I think we have just barely started. To put in next 5-year terms, this is the start of revolution. We'll have to solve problems of much larger size. And I see that that's going to be possible. And my research group is working very hard to try to achieve that. And we need a lot more people. And also with people, we need ideas. So where are these ideas going to come from? These ideas are going to sit at the intersection of theory, statistics, and systems. I'll sketch out a little bit. And what I will end with is, to make any revolution, you need challenge problems. So what are these challenge problems? Let's try to see what we should be able to solve in 2025. Can we compute reliability of Los Angeles transmission grid? Right now, we can handle small cities, but LA is a really large city. That's where the Hollywood is. So can we handle reliability of such a large LA metropolitan area? In case of neural network, right now we can handle networks with hundreds of neurons or few thousands. Can we handle networks that have hundreds of thousands of neurons? In case of security, can we handle measurement of C++ programs with 1,000 lines of code? As I mentioned, getting there is going to require ideas from different technical fields. And let me sketch some of the ideas that I think are going to be crucial. First is at the level of systems. We need to do a tighter integration between solvers and algorithms. The entire algorithmic framework is making use of the set solver, but these are not regular calls. We know there's a structure in these calls, and we need to work on getting a tighter integration. Over the last 2 years, we have seen that pursuing a tighter integration leads us to interesting problems at the level of systems and very remarkable improvements. At the level of theory, well, we need way of constructing more efficient hash functions. And we see that there are very interesting connections to isoparametric inequalities and coding theory and so on. So this is what's going to make the algorithms much better, okay? And then finally, how do we know that the algorithms are computing correct answers? And to do that, we need methodology to verify that our approximate counts are correct. And this is an interesting problem. It's on inside, and it's on. Just to remark that a similar problem in context of set, where we wanted to say whenever set solver says, oh, the formula is unsatisfiable, can you give me a proof? And that has led to a beautiful line of work over almost a decade, resulting into lots of very interesting insights, theory, and as well as system building. So I think these directions are just few of the directions that I wanted to sketch out, and all of these have potential to require new theory, new algorithms, and new systems. With that, I would like to conclude. I'll be very happy to take any questions now or over email. I would really like to meet all of you in person, but these are different circumstances. Thank you for your attention.
Thank you, Prof. Kuldeep Meel. So, any questions from our audience? So, if you don't want to, okay. So there is one question from Mahe in the type channel. Question one. The question is that why approximate counting is attractive, even if approximate counting is still practically difficult.
Yeah, so that's a very good question. The reason that it is still, of course, it's a hard problem. So we are not going to, approximate counting is still going to be harder than just checking whether there exists a solution. But approximate counting is still much, much easier compared to trying to do exact counting. So counting as a problem is important. And at this point, we want to ask, well, if we cannot do exact counting, can we at least do an approximation? And these are not any kind of approximation, right? So one thing that is worth remarking again is that if you can see the screen, I hope you are able to see the screen, right? So as you can see that the estimates that we are interested in here, these are estimates with rigorous guarantees. So while we don't have an exact answer, this is an estimate that says that with probability at least 1 minus delta, the answer is within these two bounds. So it's not as good as knowing the exact count, but it's also an approximation that can give a lot more information because it tells you the interval within which the count is, and this interval is adjustable by the user. So if you want really small interval, well, you are going to pay more, but you get to define that. So in some sense, this gives a better handle for the quality of answer that you really require versus the time that you are ready to spend on. Okay, so this to me is a better formulation in the sense that in case of exact counting, this is all or nothing. Either you get the exact count or you don't. Here you can say, well, I don't want to spend too much time, so I'm going to relax epsilon. I'm going to say I will have smaller epsilon, and can you still get the count?
Okay, thank you, Prof. Any more questions? You can unmute yourself and directly ask Prof. Kuldeep.
Yeah, so please feel free to ask. One of the things, as I mentioned to you, that one of the biggest development in formal methods and set solving came from a PhD student really not agreeing with everyone else, right? So being able to come up with new insight that led to the whole entire conflict-driven closed learning paradigm. So when you are a PhD student, this is kind of the right time for you to question everything that you hear.
Okay, you may like, maybe the audience would like to email you offline or free access. So thank you, Prof. Thank you for an interesting talk. Okay, thank you again. Thank you, audience. So we will have a 5 minutes break and then go to the next talk.